Alô?
Hi everyone, nice to meet you all. I'm the last one. So, my name is Elaine. I am a PhD student in the Bioinformatics and Machine Learning research group that is part of Computer Science Program and Computer Department at Federal University of São Carlos. CNPq and CAPES finance my PhD project. And today I'll talk to you about my paper called Community Detection for Multilabel Classification. These are the co-authors in my paper. Ricardo CERRI, my supervisor, he's here. Alan and Mauri FERRANDIN. So, multilabel classification is a predictive task of machine learning that aims to build a model that predicts multiple labels for an instance. One of the challenges in multilabel classification is identifying, modeling, and exploring label correlations. The literature says that there are correlations between labels in all multilabel problems as if they are natural in the multilabel data. Then, if a model learns these correlations, a model can predict better a label, and the predictive power of the classifiers can be improved. And multilabel classification, multilabel problems can be treated in two approaches, mainly. The global approach that adapts existing algorithms or develops new ones and uses information from all labels to deal with the problem. So it maybe is more relevant and important in local information, local correlations. And in our project, we consider as local approach only those methods that divide the multilabel problem into several binary problems. So as local approach learns each label individually, finding the correlations between them is impractical. So in our investigation, we try to use the advantages and mitigate the disadvantages of both approaches, trying to make a better use of the local and global information. And we propose an approach that is between them, an approach that we call hybrid partitions for multilabel classification, or HPML. So in this figure, we show the partitions that we introduced in our work. The squares represent the partitions, which are label partitions. The circles represent the clusters, label clusters, and the diamonds are the labels. So here, I want to highlight that we use labels to clusters. Because of that, I say label partitions and label clusters, we do not use the input attributes, we use the label space only, because we want to model the correlations between them. So the first figure 1A is a global partition, which is based on global approach, and only one model is induced in this case. All labels are clustered together. In figure 1B, we have the local partition based on local approach, where each label is in a different cluster, and one model is induced per cluster. And finally, we have figure 1C, that is our proposal, the hybrid partition. And this partition is between the global and local ones, and are composed of disjoint correlated label clusters. So, these partitions can be generated by an approach that models the label correlations and partition the label space accordingly, and therefore you can obtain several and different of those partitions with different number of clusters and different number of correlated label within each clusters. So, my goal was to develop, implement, and evaluate an approach capable of that, and also that can choose one of those hybrid partitions that can better optimize the classifier performance. So in figure 2, we have the flowchart for our approach. Our approach identifies, builds, validates, and tests hybrid partitions for multilabel classification using community detection methods, and is composed of 6 steps. First step, we divide the multilabel data in training, test, and validation. We use a specific stratification for multilabel problem, and we also split the label space from the train to use in step 2 for model the label correlations. So we choose to use community detection methods because they can systematically encode interactions between data and find relationships between them. And also they allow us to do both model label correlations and partition in the label space. And in this context, with multi-label classification, the vertices are the labels and the edges are the correlations between them. So a community mainly is a set of vertices with many edges inside the community and some edges outside the community. So for us to use community detection methods in this context, we had to build a network from vector-based data, which makes it possible for us to establish links between all pair of labels with weights from a similarity matrices. So here in this step 2, first we obtain 2 similarity matrices from Jacker Index and Rogers Tanimoto, and then we use those similarity matrices with a technique called sparsification to cut the edges with small weights from the graphs. So we build the graphs and then we apply sparsification. We use one sparsification based on K and K nearest neighbor that cuts the edges with small weights that is not part of the neighborhood. And also we use a threshold sparsification that cuts a percentage of those edges. And in our case, we use K equal to 1, 2, and 3. And in case of threshold, first you cut the self-loops, then we cut 10% of the edges with small weights. So at the end of step 2, we obtain 10 label accuracy graphs that we use in step 3 as input for the community detections. So we apply for non-hierarchical and 3-hierarchical community detection methods. And in the case of hierarchical methods, they generate dendrograms that can be cut at several levels and thus produce several partitions. And in the case of the non-hierarchical methods, they produce only one partitions. So at the end of step 3, we have several partitions, and then in step 4, we choose one of those hierarchical and non-hierarchical community detection methods to generate the hybrid partitions. And for that, we choose the one with the highest modularity. Also in step 4, we build the corresponding data sets for each partition generated. And in step 5, we validate all hybrid partitions generated only by the hierarchical community detection methods. And for that, we use silhouette coefficient for this criterion of selection. Then the partition with the highest value for the silhouette coefficient is chosen to be tested in step 6. So in step 6, we test all those partitions, and we could use here any classifier, but as we need to do a properly comparison between the partitions, global partitions, local partitions, hybrid partitions, and also random partitions, we need to use a classifier that allow us to deal with different type of composition of cluster, like a cluster with one label, cluster with 2 labels, and so on. So here we need to investigate the improvements from hybrid partitions in relation to other partitions. And because of that, we need to use exactly the same classifier to be with the same bias. So for that, you use class framework, which has these features. It allows us to do the binary, the multi-label classification, and is a predictive cluster tree for hierarchical multi-label classification that is well established in the literature. So about the experiments, we use 20 data sets, benchmark data sets, multi-label, from 5 different domains with a variety of characteristics. And also we use tenfold cross-validation in our experiments. So we have here the space label, varying from 4 to more than 100 labels. Here we have the methods, so the global partition, local partition, and also 2 types of random partitions generated with random graphs and K-NaN sparsification, with K being random. And the other methods are based on partitions generated with the community detection methods. We also evaluate our results using the MLP, missing label problem measures, and McGrath-Young multi-label evaluation measures. So, About the results, here we have the results about the most chosen community detection methods. Walk trap was the most chosen one, hierarchical community detection method for Jacquard and Rogerson and Moto with KNN, and also Randall with KNN and threshold sparsification. InfoMap was the most chosen non-hierarchical community detection method for both sparsification and all graphs. And also we have edge between us for threshold sparsification with Rogerson and Moto. And about the best chosen hybrid partition, we obtained that a partition with 2 clusters was the most chosen one for most data sets and in most methods. So this partition with 2 clusters is really closer to a partition with 1 cluster. The case is the global partition. So this can be one of the reasons that our performance results were very competitive between other partitions, and also overcome the global partition, but for some data sets was not superior in relation to the local partitions. Here we have the win-loss type plots that mainly shows us how many methods a method beats the others. In general, we have that local partitions obtain the best results, while global partition obtain the worst results. And for the random partitions and hybrid partitions, we got a similar behavior. Random partitions and hybrid partitions was better or superior than the local for some data sets, and superior than the global for most data sets. So we conclude for this that the hybrid, random, and local partitions are competitive between them. And for MLP and McCarthy-1 value-is performance, we have that the best value for MLP is a value near to 0.0. So a value higher in this measure indicates that not all labels was not learned, not predicted by the classifier. And here we obtain an average of a value about 0.9. So indicates that the most labels are not learned, not predicted by the classifiers. And this reflects in McCarthy-1. McCarthy-1, the best value is 1.0. And here we obtain values near 0.3 in the average. So most of labels are not predicted. In consequence, the measuring McCarthy-1 had a not good result. So we can conclude of this performance analysis that our approach managed to obtain hybrid partitions between the global and local ones that can improve the classifier for some cases. And the low level of correlations between the labels in some data sets can be a reason that even random partitions obtain better results than the traditional approaches. And we also can conclude that the global and local approaches may not learn correctly the label correlations. Yet, our approach worked. So, we here have the statistical test Nemini and Friedman results. The left side we have the best methods, and the right side the worst methods. So for McCarthy-1, there is no statistical difference between local partitions and random partitions for non-hierarchical methods, and also for hierarchical partitions. And there is no difference between global and random partitions with hierarchical, non-hierarchical methods, and some of the hybrid partitions generated with hierarchical. But for both measures, we have that there is differences between local and global partitions. And for MLP, we have there's no significant differences, statistical difference between local, random, and hybrid partitions, and also between the partitions generated with both of community detection methods. So, for the conclusion and future works, we concluded with our investigation that hybrid partitions obtain better or competitive results in several data sets. The average performance remained competitive for most methods and data sets. And independently of the partition that we use in our investigation, there is no vast improvement besides the competitive performance values. Most labels are not learned by the classifier, even by the traditional approaches. And the classifier still has difficulties in learning the several labels at once and predict them correctly. So we conclude that global and local approach may not learn correctly the label correlations. With this, we see that multi-label methods need to improve because regardless of the partition we use, or if the correlations or not considered, explored, we cannot state with absolute certainty that they are correct to learn the correlations and the labels. Still, and also random clusters, random partitions with random label clusters, then a global partition. So for future works, we pretend to explore other multi-label evaluation measures, other classifiers, and other data sets. So thank you very much for your attention, and sorry eu falei muito rápido.
Tenta pegar mais
Elaine, parabéns pelo trabalho. Você mostra uma outra abordagem, além da local e da global, né? A híbrida, né? E é claro que o usuário ele gostaria de saber quando deve usar uma ou outra. Quando você apresenta os resultados, você fala, olha, o híbrido foi melhor na maioria dos casos que local, ou pior em alguns casos, você mostra dessa forma. Mas assim, tendo uma instância, por exemplo, o leitor, o usuário gostaria de saber qual que eu devo usar. Então, a minha pergunta é um pouco nessa ideia. Quando que eu deveria usar a sua abordagem? Quando ela apresentaria vantagem, de acordo com as características do seu enfoque, né? E quando eu não deveria usar?
A minha abordagem, você disse?
Isso, a híbrida. Quando você acha que vai falhar e quando você acha que vai... Isso é o que? Você fala, pode usar. Dadas as características da instância.
Então, tem várias controvérsias na literatura a respeito disso. Não existe, na verdade, um ponto final dizendo que se deve usar uma abordagem global, uma abordagem local, e tem alguns trabalhos mais recentes que estão agora começando a explorar isso que a gente já está investigando. Então, não tem assim uma resposta, é isso aqui, mas o que influencia muito são as questões do nível de correlação que a gente pode encontrar no dataset. Tem alguns autores que falam que os benchmarks, né, que a gente usa de multilabel, eles têm um nível muito baixo de correlação, e que não é possível explorar as correlações. Mas no nosso experimento a gente viu que se houvesse um nível de correlação, a gente consegue encontrar sim uma partição que é melhor do que a global e local e você pode usar, né? E tem algumas áreas de aplicação que estão usando, inclusive, uma abordagem similar com a nossa, como é o caso de DTI, que é Drug Target Interactions. Então, assim, eu acho que precisa fazer uma análise preliminar, né, do que é o problema que você quer resolver e aí identificar se a nossa abordagem realmente se encaixa para resolver aquele problema, né? A gente testou com vários datasets diferentes, de vários domínios diferentes. E para cada um deles a gente teve resultados diferentes, né? Então, precisa também fazer mais experimentação, né? É uma coisa que ainda a gente está começando.
Parabéns pelo trabalho, pela prestação. Você decidiu gerar as partições usando uma técnica de detecção de comunidades, né? Mas eu imagino que você poderia ter modelado isso com o programa de cluster, né? Aí eu queria que você comentasse assim, quais são as vantagens que você fez disso e quais são as possíveis desvantagens também.
De usar o cluster, você diz?
Essas duas abordagens, você escolheu detecção de comunidade, mas por que você escolheu detecção de comunidade ao invés de cluster, e se isso aí pode ter algum efeito negativo?
Na verdade, a gente tem outros experimentos publicados com outras abordagens. Então, tem um paper publicado no JCMN 2021 que a gente usou o algoritmo hierárquico cooperativo, né, para gerar as partições. E lá a gente teve resultados similares. Tá? Mas os valores, a gente usou outros datasets, não foi exatamente esse, tem alguns lá que estão aqui também. Mas, assim, o resultado que a gente teve com o algoritmo hierárquico e também com os métodos de detecção de comunidade levam às mesmas conclusões. Né? Então, assim, novamente, eu posso usar qualquer técnica de modelagem para modelar os rótulos e qualquer técnica para particionar os rótulos. Os métodos de comunidade têm a facilidade de que eu já modelo, já particiono com o mesmo algoritmo, né? Vamos falar assim, eles são algoritmos de particionamento de gráfico que precisam da matriz de similaridade para gerar o gráfico e particionar ele. Mas, naquele outro experimento, a gente usou o hierárquico, né? E depois particionou pelos endogramas, né? E aí fez a classificação. E os resultados foram similares. Né? Então, assim, a gente talvez precise testar ainda com outros métodos, ou talvez, se for o caso, dar um trabalho futuro, fazer um método próprio que talvez, né, consiga dar uma resposta, sim, fantástica. E mais uma vez, eu queria dizer também que os datasets têm uma certa influência nesses resultados, pela questão das correlações das próprias características. Tem datasets que a gente sabe que não tem muitos conjuntos de rótulos diferentes. Né? Então, eles não vão ter, os rótulos não vão ter muitas, não vão ter correlações muito fortes entre eles, e isso pode impactar no resultado final.
Parabéns, Elaine, para você e pelo professor, seus colegas. O que a gente deve dar para você?
A pergunta. Então, o nosso trabalho que a gente vem investigando já há algum tempo, a gente descobriu um potencial leque, gap, assim, que precisa de mais atenção, né? Que é a questão de que a literatura ela sempre recomenda o uso de métodos da abordagem global, né? Dizendo que são os melhores para resolver o problema multirótulo, que você aprende todos os rótulos de uma vez só. Mas o que a gente está vendo, né, com os nossos experimentos, nossa investigação, é que existem outras formas de você resolver isso que dão um bom resultado. Inclusive, o que a gente tem obtido de resultado é que as partições aleatórias, com rótulos aleatoriamente postos nos clusters, eles conseguem ter um resultado melhor do que a global. Né? Mas, assim, o mais interessante que a gente conseguiu também descobrir é que a local consegue ir muito melhor do que a global. E tem alguns outros trabalhos na literatura que também apontam isso. Né? Por isso que eu até comentei que não existe um consenso sobre qual seria o melhor de ser utilizado. Então, assim, é um tópico que a gente precisa de uma atenção maior, de uma investigação maior, né? E é uma das grandes contribuições que o meu trabalho traz para o estado da arte aí, na área de multilabel.